would like to invite another speaker, Moncy John. He's from Mahatma Gandhi University, Kerala, India, and his talk will be on modified cosmology and gravity theories. Moncy, you can share your screen.
Thank you, Sada. Nuances of cosmologies. By cosmology, what we mean is the scale factor of varying. The cosmological models. By costing, what we mean is the scale factor varying linearly with time. And we are considering only the FRW cosmological models for the time being. The background space-time, the background universe. So the condition, we note that the zero active gravitational mass condition is rho c squared.
Recording in progress.
So the zero active gravitational mass condition is rho c squared plus 3p equal to 0. This condition can be equivalent to the equation state because p equal to -1/3 rho c squared. The solution of the Friedmann equation in this case is A equal to mct. It is varying linearly with time. M is a dimensionless constant. C is speed of light. M is square root of k by omega minus 1, where omega is the total density parameter. We can take all the three curvature parameter values, k equal to 0 plus or minus 1. The spatial geometry can be closed, open, or flat in this case. Regarding the value of m, we can see that it is equal to 1 when omega equal to 0. In that case, we have to take k equal to -1. So, looking at the equation, m can be equal to 1. Similarly, when omega equal to 1, we can again, k should be equal to 0. So, there is a possibility for putting m equal to 1. And for omega equal to 2, there is k equal to +1. So that again, in these three cases, we have m equal to 1. But in other cases, normally, m is a parameter. It's a free parameter. It can take even infinite values, nearly infinite values as omega tends to 1. So let us now consider some special cases of this. If we are considering only the single component cosmic fluid, in that case, the equation state parameter is -1/3, that is rho varies as a to the power -2. But this kind of a component is exotic, and such a model is not physical. Another special case is that of an empty model where rho equal to 0, k should be equal to -1, and you can write a equal to ct. But of course, this is unphysical, for it is an empty model. Thirdly, there is a matter-antimatter symmetric cosmology. Antimatter has negative active gravitational mass, so the total active gravitational mass will be 0. But there is no direct evidence for this scenario. Instead, if you have two components in the cosmic fluid, there is a possibility for a viable cosmological model, which we call the eternal costing model. Here, rho is the sum of a matter term and a lambda term, the cosmological constant. The corresponding pressures are also Pm and P lambda, the sum of these. Pm is the matter equation state with the W, and P lambda has the equation state parameter -1. We can take k equal to +1 or -1 or 0. If you are considering the zero active gravitational mass condition, this uniquely gives the ratio between densities of matter and lambda, or the ratio between density parameters between matter and lambda equal to 2/1 plus 3W, where W can be 0 or 1/3. So this ratio should remain a constant. That means both matter and lambda densities must vary as a to the power -2 to keep this ratio a constant. And that ratio is a constant of the order of 1. So there is no coincidence problem in this model. Because of this matter and lambda varying as a to the power -2, the components cannot be separately considered because matter should vary as a to the power -3 and rho lambda should remain a constant. But in this case, they are not separately considered. There can be creation of matter as lambda decays. This model was discussed in this paper. And let me now consider the other eternal question models discussed in the literature. The classic Milne model of 1935. It is a non-generalized model. It has eternal linear expansion, but it's not a realistic model because it does not consider even gravity. Even in the very early epochs, gravity is not considered to be contributing to the cosmic evolution. Another eternal question model is the RH equal to CT model, Melia and Shevchuk in 2012. We have K equal to 0. This is actually the K equal to 0 case of the eternal question model. And recently, there is the hyperconical model by Monjo in 2017. It can take all values K equal to plus or minus 1 or 0, and it is eternal question. But when considered to these eternal question models, there are certain quasi-eternal question models. That is, the Osataha model with the K equal to plus 1 is quasi-linear. That is, it is linear or this eternal. This linear or costing only in the early universe. Similarly, the Cole and Chen Wu models in 89 and 90, they have K equal to plus or minus 1 and 0. They are quasi-linear and costing only in the late universe. In this case, I would like to consider one more model, the bouncing and costing model, which has the scale factor varying as this expression. Here, A0 is the minimum size of the universe at T equal to 0. That initial moments can be considered to be a quantum epoch. But in the classical epoch, that is when CT much greater than A0, this is eternal costing with the K equal to plus 1. This bouncing and costing model was discussed in these papers. Please note that these papers appeared even before the supernova data came in 1998. A graphical way of looking at this is this. We have a previous contracting phase for such a model. A bounce happens at nearly the Planck time, and thereafter it evolves in a costing manner. Now we discuss the solution of cosmological problems in this models. In general, the costing models. The models we discussed so far are all singular except the bouncing and costing model. So we can say there is no singularity problem in the bouncing and costing model. And there is no singularity problem in this model. Regarding the flatness problem and the horizon problem, we know that in the lambda CDM model, these problems are solved due to inflation. But in this model, the eternal costing model, the total density, including individual components, all vary as a to the power minus 2. So it can have K equal to plus 1 or minus 1, and there is no fine-tuning problem here. Hence, there is no flatness problem. Similarly, the horizon problem is absent in the eternal costing model. A more serious problems in the lambda CDM model are the cosmological constant, the coincidence, and the fine-tuning problems. The origin of these problems can be seen from this diagram. In the lambda CDM model, the radiation and matter terms vary as in the blue line, but the vacuum energy, the brown line, vacuum energy falls from a very huge value of 10 to the power 94 gram per centimeter cube to an abysmally small value of 10 to the power minus 29 gram per centimeter cube. And that is in the very small time of inflation of the order of 10 to the power minus 35 seconds. But thereafter, this vacuum energy or the lambda tape or the dark energy with this small, very small value, it should continue as a constant, as in the red line, and only in the present epoch, they are nearly equal. So this is actually a very extreme coincidence, can be only an extreme coincidence. And especially the vacuum behaving in this particular way can be achieved only by some extreme fine-tuning. So this is the origin of these problems. But in the eternal positive model, since all vacuum and ordinary matter are all varying as a to the power minus 2, there is no coincidence. There is no cosmological constant problem. There is no coincidence problem, or there is no fine-tuning problem in this case. One serious problem with the lambda CDM model is the synchronicity problem. The synchronicity problem can be understood from this diagram. Here, the red curve represents the evolution of the scale factor in the lambda CDM model. One can see that at present, if you draw a tangent to the curve, that curve may meet exactly the point of the moment of Big Bang origin. Mathematically, this condition can be written as ht equal to 1. So the situation in the lambda CDM model is that the tangent can meet the Big Bang origin, and that happens only once in its history, and that is precisely now. But in the eternal positive model, ht equal to 1 is a prediction because the evolution is linear. So this is a prediction. So there is no synchronicity problem in the lambdas, in the eternal positive model. Lastly, we consider some cosmological observations. A very important observation is that of the type 1a supernova. In the lambda CDM model, this unnatural dimming of type 1a supernovae is interpreted as due to a late accelerated expansion of the universe. To see how it reaches that conclusion, let us look at this equation for the luminosity distance. We have to do this integral, and on the left-hand side of this integral, you have to put the expression for scale factor as a function of time. In the lambda CDM model, A of t is expressed in terms of omega m and omega lambda. And the analysis gives values of omega m and omega lambda such that that indicates accelerated expansion. However, this analysis can be considered only as a model-dependent analysis. What do you mean by a model-independent analysis is this? Instead of a scale factor A of t as a solution of a Friedmann equation, we can think of A of t as a Taylor expansion about some time, t0. So the equation will look like this. We can truncate the series to some finite number of terms. There are the parameters in this model. H0 is the present value of Hubble parameter. Q0 is the present value of deceleration parameter, R0, S0, etc. And in these two papers in 2004 and 2005, the bias theorem was used to evaluate each of these parameters by marginalizing the likelihood function over the rest of the parameters. And what we see, the result is this. In 2003, the 54 all SCP supernovae was used as the data, and the analysis was done. The marginal likelihood for deceleration parameter was obtained in this way. One can see that Q0 equal to 0, there is a significant marginal likelihood, even for Q0 equal to 0. And that was in 2003. The paper was published in 2005. But
2 minutes
later,
left.
Another data, the constitution data was used. And what we see that there is a very significant high value of likelihood for the value Q0 equal to 0. So this supports the eternal constant model. And lastly, I want to mention the early bright galaxies observed with James Webb Space Telescope. The recent observations of early bright galaxies with JWST rotates that in the universe, galaxy formation has taken place much earlier than expected in the lambda CD model. This is the problem with the early galaxies in the lambda CD model. The significant papers are these. And there are redshifts 13.2 galaxies which are spectroscopically confirmed as z equal to 13.2, 12.6, and so on. So the problem with these galaxies, the farthest galaxies ever observed, is that in order for them to appear in such a massive manner, over 1 million solar masses, they might have built up their masses in only less than 300 to 400 mega year after the Big Bang, as per the calculations in the lambda CDM. But the same Hubble parameter value can be used. See, this is quite unexpected as per the current understanding of galaxy formation. If the same H0 value is used, on the other hand, in the eternal costing model, even a universe at redshift Z12 has ample time, that is 1070 mega years for galaxy formation. And this suggests that in the early universe too, data support the eternal costing model when compared to the lambda CD model. I stop here. Questions are now welcome. Thank you all.
Thank you, Moncy. So, any questions?
Oh, I think Eric has a question.
Yeah, we have only 10 minutes left for the questions.
So my question is, in any expanding model, we can use the Tolman test of surface brightness to distinguish between expansion and non-expansion. So for both the Hubble results and now for the James Webb Space Telescope results, there is absolutely no difference in the surface brightness, which is an observed, directly observed quantity for galaxies at high redshift up to now up to 8 or 10, and galaxies in the local at z equals 0. So this seems like a clear-cut contradiction of any expanding model. How does hosting cosmology deal with this contradiction in surface brightness?
Actually, I'm sorry, I can't comment on that, the astrophysical part of that question. Actually, we have discussed the calculations as per the papers on early bright galaxies. Such details, I am sorry, I can't comment.
You haven't looked at this data?
First slide.
There was some comment or maybe question. What could be the signature of costing model in CMB? Can we constrain these parameters using, let's say, Planck dataset?
Actually, the RH equal to CT model by Melia and collaborators have worked on a lot of cosmological observations, including CMB. So the early universe, as per the lambda CDM model or the eternal costing model, is yet to be worked out because, in my opinion, this particular case, all the components in the cosmological cosmos vary as a to the power -2. So that is the basic ansatz we have used to arrive at the eternal costing model. So in that case, all components, including lambda or matter or radiation, whatever, must vary as a to the power -2 means the early universe must be reworked in this model, and many things are yet to be worked out. In the RH equal to CT model, the variation is different. So I cannot compare this with the RH equal to CT in that case, early universities. So this part is not yet worked out for the eternal costing model.
All right. Indranil wants to ask something. Yeah, Indranil.
Yes. So I wanted to ask a related question, which is you probably not worked out either, but is related to the Big Bang nucleosynthesis. So how does that work in this model? Like, do you have any idea? Like, do you get A proportional to T even in the first few minutes of the universe in this model?
Yeah, right. That's
in this model, that is.
So throughout the same scale factor, I'm getting an echo, sorry. Throughout the evolution of the scale factor, evolution of the universe, the scale factor is the same, A proportional to T. And all components in the cosmic fluid, there can be creation of matter from lambda. That is one important aspect of this model. So there is not yet any complete discussion of nucleosynthesis or other cosmological observations. In this model, only the large-scale behavior is studied. The details are not yet worked out.
Can I ask a question related to the late universe in that case?
Yeah.
So which of the tensions we were discussing earlier can be addressed with a model like this? So, if, for example, regarding the faster growth of structure in the KBC void or in El Gordo at redshift 1 approximately, would these models help with that at all? Because the age of the universe would be much the same, right, in this model, right?
The age of the universe is given by actually a characteristic expression for this model is HT equal to 1 because the
exactly. So the age of the universe will be much the same as in lambda CDM, right, today. But would you be able to?
No, actually, it's approximately the same, maybe slightly
it's within
more
a few percent.
The lambda, yeah.
That's within a few percent. But what I was asking is, like, would it help with anything at the perturbation level? So regarding the growth of structures in the universe, would these models be able to help with explaining the KBC void or the El Gordo cluster?
Yeah, I think they are all problems really worth discussing in this model, but those details are not worked out. All these areas.
Okay.
By Melia, I think something is made. By Melia.
Yeah, Melia has done a lot of work. That is a special case of K into +1. K equal to 0 case of the eternal costing model. But even though it is that special case, a lot of cosmological observations are studied and analyzed by media.
And some question by Juan. You can unmute yourself and ask.
Yeah.
Hi, Moncy.
Hi.
Could you comment on the possibility that the universe behaves as a huge black hole, which mass is rising as its radius, as energy?
Actually, that
energy.
Okay. Actually, that calculation contains very peculiar and very significant information. That observation is very important. But regarding I think coincidence for me. I can't how to connect it with the black hole situation. I'm not clear. Sorry.
Thank you.
Maurice wants to ask something.
Yeah, if I understood it correctly, you also take the this approach down to the early stages of the universe, this coasting solution. Is that correct?
Right, that's right.
But then how do you satisfy the observed BAO angle? Because that depends on having an exact timing in the surface of last scattering.
Yeah, I told you this, such details of the model are such, apart from the RH equal to CT model, these details are not worked out in the present model. So it is some basic arguments. It's the modified Chen-Wu ansatz that we arrived at this model. That the scale factor in the classical epoch, in the quantum epoch, we can have a different evolution. That is much when the scale factor is much greater than the Planck length, but otherwise it is costing. That is the conclusion we have reached from that ansatz. But the details have to be worked out. Sorry, I can't say.
I think it's from the previous question, I think. So.
Yeah, thanks. I was just wondering, this model still requires dark matter, right?
Yeah, that's right.
Yeah.
Yeah.
There. Yeah. Okay.
That's right.
Yeah. So the same caveat applies to, as I said before, the problem with the dynamical friction.
Yes.
That's right. These are only the global features which I have described, not the fine details.
Just a comment. The major critical point of this type of model, costing model, is of the zero active gravitational mass condition. And the solution for this is to change the general relativity to be valid only for perturbations with respect the background metric. So the background metric is evolving by itself as a geometrical manifold, and the energy of the space-time is not affecting to the linear expansion. So dark matter and dark energy are irrelevant in this type of models.
Is it a question? I think it's a comment. Am I right?
No, it's a comment. Sorry, it's a comment to complement.
So, any more questions? Okay, then we thank you, Moncy, and then we move to our next speaker.